All right. Good afternoon, everybody. Let's begin. You probably saw my message yesterday that I had posted the homework assignment and the notes on Blackboard. So you can get started on the homework assignment. Today we're going to be continuing our discussion on flow resistance, which is taken from sections 1 through 3 in Chapter 7. We'll work a couple of examples today. And any questions before we get into it? All right. I will note one thing, is that yesterday when I posted the assignment, I decided to clarify the problem statement number 8. So the problem isn't any different, but I added a couple of extra things to the drawing. So if you downloaded or printed the assignment immediately after I sent the message, you may double check to see whether it's this drawing where I've said, and they clarified that the unknown, is what's the elevation of the water in the tank. The way the problem statement was written before kind of made it seem like the unknown was the pipe size. The pipe size is given. What you're trying to find out is where's the water at in the elevated tank. So I just wanted to draw your attention to that. Okay, so this is meant to be a force balance of an element of water that's inside of a pipe. And so what we're going to do is consider, why is the pressure lower in the downstream direction? When water is flowing through a pipe, kind of quantitatively, we know that the pressure decreases because of pipe friction. You know, we've said that lots of times before, that the interaction between the water and the roughness elements in the pipe material is causing the decrease in pressure. But let's look at it from a force balance standpoint. And so this force balance is starting with the sketch, and if we have the external forces that arise from the pressure acting over a certain area. And we did that in Chapter 6 when we were discussing momentum. Remember that if we cut a pipe and we just look at the fluid that is within a control volume, then even if the water continues on the other side of the control surface, we treat it as though it's an external force, and so P1 times the cross-sectional area is like a force that's pushing this element of water to the right. So just to clarify, what we're looking at isn't the pipe. It's the water inside the pipe. So we're looking at just some amount of water inside a pipe, and it may be that the pipe is inclined in this case. You'll notice that they're kind of looking at the effects of how inclined the pipe is. So the angle is alpha, and so what that means is that the weight of the water ordinarily would go straight down, but because this pipe is inclined, then the weight of the water in the direction of flow is multiplied by the sine of alpha. And so the sine of alpha is what's going to account for the component of the water's weight that's acting in the direction from 1 towards 2. So remember, this is all a force balance. So we have the forces that are arising from the pressure times area on the left, which is in the same direction of flow. Then there's some water on the other side of this element of water pushing in the opposite direction. And so, you know, this is a continuous body of water that we've just cut with an imaginary line. We've cut with the control surfaces. And so P2 times the cross-sectional area at 2 is opposing the flow, since it's in the opposite direction. So you'll notice the minus sign here is saying it's as though that's a force that's acting in the opposite direction from the original pressure times area force. The weight of the water element in the direction of flow is plus, because it acts to the right. And then this last term here is kind of the important one if we're talking about resistance. What that is the shear stress, the perimeter, and then the length of the pipe segment. And so what it is it's the force that's applied by the pipe to the outside surface of the water. It's the shear force that arises out of a shear stress. And so it's kind of why the effect that causes the pressure to be lowered downstream. Like if we were going to go one step beyond just the knee-jerk response of saying the pressure is lower downstream because of pipe friction. You know, like if somebody said, well, tell me more about that. Tell me more about the pipe friction. Well, then what you'd say is it's shear stress that's acting over the area of the liquid element. And so it's the cross-sectional, excuse me, not the cross-sectional area, the surface area. And so perimeter is the circumference of the pipe. So it's the outside length multiplied by the length L. So L is the distance between 1 and 2. Multiplied by the shear stress. And so if shear stress has units of force per area, like newtons per meter squared, and then we multiply it by some area, the outside area, kind of like the label of a soup can, is an area that you could flatten out and you could measure that area. Well, it would be the perimeter of the soup can multiplied by the length of the cylinder. So this is in equilibrium. If we have steady, uniform flow, then those forces are going to be equaling each other. And then that's how we account for the difference in pressure downstream. And so we can experimentally determine what is the shear stress by measuring all of the other parameters physically. And you can take a pressure transducer, connect it to a pipe, and you can see what is the pressure at location 1. And at some downstream location, you could put in another pressure transducer and physically measure what is P2. And of course, from the pipe diameter, we know that we could identify the cross-sectional area. We could measure the pipe length by knowing what is the fluid and its temperature. That gives us gamma. The angle that the pipe is inclined can be measured directly. And so really the only unknown parameter would be the shear stress. And so it's not, the shear stress isn't something that we can easily measure directly, but in an equation like this, where we know that flow is steady and uniform, we could measure everything else, and therefore we could calculate the shear stress that's causing the change in pressure. So does everybody feel like they understand this force balance? Any questions about that before we continue? All right, so some additional definitions if we extend what we thought of so far. Now, the change in pressure divided by gamma, that's the definition of the head loss due to pipe friction. So H sub F is the change in pressure divided by gamma. And hydraulic radius, R, is the cross-sectional area divided by the wetted perimeter. So from this expression, what we could do is we could relate the head loss and shear stress. Now, by the way, the change in pressure between 1 and 2, it's partly because of an elevation difference, and it's partly due to energy loss. So here, where we were saying that the pressure change divided by gamma is H sub F, that would be for a horizontal pipe. And just keep that in the back of your mind as we go through the rest of this kind of derivation, is that for a horizontal pipe, the change in pressure is only caused by the head loss due to pipe friction. Okay, so then what that allows us to do is relate shear stress and energy loss. And the geometry of a circular pipe, if it's flowing full, and we have some pipe that has diameter D, then hydraulic radius is the area divided by the wetted perimeter. And so area of a circular pipe is pi d squared divided by 4. And the perimeter of a pipe, we go around the outside edge, it's just pi d. That's the formula for perimeter. And so if the pipe is totally full with water, meaning that the water is up to the top and there's no voids, then the hydraulic radius is just d divided by 4, because the pi d in the denominator cancels out the pi and one of the d's in the numerator. So if we have a circular pipe that's flowing full, then the substitution that's made here is instead of hydraulic radius, we've substituted in D and where's the pi? Oh, I'm just not seeing it. Yeah, it got canceled out. Okay, so now the slope of the energy grade line, S sub F, is defined as the slope of the energy grade line. And so that's the magnitude of the energy loss divided by whatever the length of the pipe is. And so what this is all building to is the relationship between the shear stress and the slope of the energy grade line, S sub F. Now, by the way, this semester there's going to be a couple of different S's. There will be S naught, which is the slope of a channel. There's S sub F, which is the slope of the energy grade line. And later in the semester, we'll have S sub W, which is the slope of the water, if it's open channel. What you need to know for now is that in a pipe, if you have steady, uniform flow, that the physical slope and the slope of the energy grade line are going to be parallel to each other. If it's open channel flow, it's parallel when you have steady, uniform flow. In closed conduit, though, the pipe slope and the slope of the energy grade line don't necessarily match each other. And we'll work an example that draws the distinction between those two. So open channel, that is steady and uniform, they're parallel. In a pipe, they don't have to be parallel. Here's the illustration of a open channel, and what it's showing is the dashed line here, the slope of the energy grade line. Since the conditions are steady and uniform, you'll notice that that's parallel to the water surface, and it's also parallel to the bottom of the bed. So the downstream channel that the water is actually flowing through. Those three things are parallel. So this formula you're going to use in the homework assignment. There are a couple of problems where the shear stress is defined, and maybe they're telling you a little bit about the channel geometry, like how wide the channel is and the depth of flow. And so with the description of the channel geometry, you'd be able to calculate what's the hydraulic radius. And so by knowing the shear stress and the channel geometry, then you can determine the slope of the energy grade line. And if you have the slope of the energy grade line and you know the length over which flow occurs, then you could calculate the magnitude of head loss, H sub F. And so let's get some practice with that. Let's say that we have a pipe that, in this case, you can see that the physical slope of the pipe is actually uphill, but since the water is flowing from left towards the right, that by definition means that there's going to be less energy on the right than there is on the left. Otherwise the water wouldn't be flowing in that direction. And so the slope of the hydraulic grade line, the slope of the energy grade line is going down from left to right. So what we have here is the diameter of the pipe is defined. And by the way, it didn't actually say it was the diameter. It just said 150 millimeter inclined pipe. So I guess it's kind of implied that that's the diameter and not the length. Usually in problem statements it'll tell you both the length and the diameter, but they don't often bother distinguishing which is which, because the really small one is the diameter and the really long one is the length. But in this case, its physical slope is going up at a rate of 0.1 meters vertical for every 1 meter of horizontal. And we know that the shear stress is 45 newtons per meter squared. So what's the slope of the energy grade line? That's S sub F. So in part A, you're going to calculate S sub F. And then in part B, what you're going to do is, once you know S sub F, find out what the head loss is, H sub F, and use that in the energy equation to find the pressure change. And so let me just write the applicable equation up on the whiteboard. We've already seen it today, but recall that H sub F is S sub F times L. Because what we said was S sub F is H sub F divided by L. So if you have the slope of the energy grade line, and you know the pipe length, then you can calculate the magnitude of the energy loss due to pipe friction that way. And then of course, our energy equation is P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus H sub F. So I've dropped out the pump and turbine terms from the energy equation because we don't have either a pump or a turbine. But we do have energy loss due to pipe friction. And so in part B, what you're going to do is you're going to find the change in pressure. So you'd move P2 over to the left-hand side, cancel out the velocity head terms, and basically apply what you know about the slope of the energy grade line to find out how the pressure is changing. All right, so we're playing around with this shear stress equation. Okay, so I put the solution up on the screen. As I was circulating around, it looked like everybody had found the slope of the energy grade line without any problem. Now, how many digits you take this to is going to determine, the amount of precision that you can report in the final answer on pressure. So you'll notice that I assumed that it was exactly 45.000 newtons per meter squared, and that's why I reported the slope of the energy grade line to 5 decimal places there. Now, the conclusion here that I've written in words that the S naught and S sub F are independent, what I mean by that is that the pipe is going up at one rate, and the slope of the energy grade line is going down at another rate. And so even though the flow is steady and uniform, the two slopes don't have to be the same in closed conduit flow. In open channel flow they will be, but in a pipe like this, the two slopes can be independent. Now we get the S sub F, and what that represents is the loss of energy per horizontal meter of pipe. So we're losing 0.12 meters of energy for every meter of pipe length. So now the pressure change in 100 meters of pipe, you may get a slightly different amount depending on how many digits you used for the S sub F. But I'm saying that my head loss is 12.23 meters. And the pressure that's downstream is different for two reasons. You'll notice that location 2 has a higher elevation, so it's going to have less pressure, partly because of the elevation change, and partly there's going to be a pressure difference due to pipe friction. But both of those are heading in the same direction. Both of those mean that the pressure will be lower at location 2. Lower because it's higher in the fluid, and remember when the hydrostatic equation says if you go down through a tank, the pressure goes up. If you move up through a fluid, the pressure decreases. And so that hydrostatic effect is incorporated into the energy equation, where we have Z on the left-hand side, Z on the right-hand side. And so, the difference in elevation between 1 and 2 is accounted for in the energy equation, but then it also accounts for the energy loss due to pipe friction, the H sub F. So I've canceled out the Z terms, the velocity terms, because the pipe diameter is constant, which means that the velocity won't be different between 1 and 2. And I assumed that the elevation at 1 was 0 and the elevation at 2 is 10 meters. So 218 kilopascals will be the pressure change downstream. You have a couple of problems on the homework where you're just relating a shear stress to energy loss. And it's just these same substitutions that you'll follow in the homework assignment. Any questions? I will make one other comment about this example. This pipe it's inclined at 0.1 meters per meter. Normally pipes aren't going to be that steep. I mean, typically in hydraulic engineering, the pipe is about the same slope as the ground. And it's pretty uncommon for a city to be built on a slope that's this steep. Like if you think about here in Huntington, there's just a gentle slope towards the river. And the reason I mention it is because we don't bother to distinguish between the inclined length of the pipe and the horizontal length of the pipe. I mean, they're slightly different. Like if you found out, like, what's the physical length of this pipe, it's going to be longer, right? Because it's the hypotenuse of a triangle. This pipe is the hypotenuse distance, and so this horizontal component of its length is going to be marginally less than its inclined distance. But it ends up really not mattering much. Even a 10% slope like this, the lengths would be so close that the head losses would be immeasurably different. And most slopes aren't nearly this steep. So we kind of neglect the difference between inclined distance and plan view distance. All right, so that's the last thing I wanted to say about this example, unless there's any questions.
Would that significant, like if you did have a town where you kind of had to have a slope like that, would that significantly impact, I guess, how much material?
Yeah.
Material? Okay.
That would be the biggest place that you'd see it, is maybe the pipe lengths would be a little bit longer.
Okay.
Mm-hmm. Okay, remember last semester we would compare and contrast Bernoulli's equation versus the energy equation. And in chapter 5, you would see Bernoulli equation used for like a pipe where you have an expanding section, where fast velocity flow is transitioning to slow velocity flow because of a rapid expansion in the pipe diameter. And where we would use Bernoulli's equation would be between 2 points that aren't very far apart. And the reason why we wouldn't want to apply Bernoulli's equation over a longer distance is that Bernoulli's equation didn't account for energy losses due to pipe friction. Bernoulli's equation was limited to fluids that were inviscid. These magical fluids that don't exist, that don't have viscosity. And the reason why we said, well, we'll apply it for an inviscid fluid is because Bernoulli's equation does nothing to account for the effects of head loss. Now, the energy equation does, through a variety of different methods. We could use the Hazen-Williams equation to approximate how much pipe friction there is, or if we want to be more accurate, we could use the Darcy-Weisbach equation to estimate how much head loss there is. But we'll use it for longer pipes where it doesn't necessarily just have to be a rapid transition. It's over a much longer distance. And we'd use either equation to predict a pressure change, but Bernoulli's equation would really only be the pressure change that's occurring due to convective acceleration. Now, a big part of what we do in this course is applying empirical equations to predict how much pipe friction is going to cause a pressure change, and working that into design. You know, figuring out how high the water tower needs to be to overcome the effect of pressure and energy loss. One of the ways that we can physically measure the change of energy as water's flowing through a pipe is with a piezometer. And just as a review, remember that a piezometer would be a location where we punch a hole in a pipe, send a tube upward, and then the water rises a certain elevation inside that tube to indicate what's the pressure of the water at that location. Now you'll notice that here the piezometer hasn't been redirected to face the flow. That's something different, where if we wanted to account for the velocity head, we could turn the tube so that it's facing the streamlines, and then that terminating streamline would cause the water level to go even a little bit higher. So we talked about that briefly when we were doing the HGL and EGL sketches, but the piezometer is just the hydraulic grade line. And so the water level is rising to account for the pressure and the elevation, but not the velocity head. In 2 points, the difference in the piezometric elevation, so the difference in the water height, is a measurement of h sub f. So that change in water elevation is due to pipe friction. And the HGL accounts for the elevation and pressure head. And the reason why the HGL decreases is pipe friction. And I've told you before that the Darcy-Weisbach equation is the most accurate way to estimate the magnitude of energy loss due to pipe friction. And so it's that friction factor F. And do you remember the first way you've learned to estimate the pipe friction factor F? Moody diagram. Good. That's right. You're also going to learn some other methods, one called the Jane equation, an even more complex approach called the Colebrook equation. But so far, you've got that Moody diagram, which is where you start with the relative roughness on the right side, you identify the Reynolds number, and the intersection of the two taken to the left axis will tell you the friction factor F. So what this formula is saying is that the change in piezometric height is the energy loss due to pipe friction, and that is estimated empirically with the friction factor times the length between the 2 points, the velocity as it's flowing through this pipe diameter, whatever the pipe diameter is, and 2g. So if we were going to apply between the upstream and the downstream location this Darcy-Weisbach equation, the velocity would have to be the same the whole way. So Darcy-Weisbach equation wouldn't work if you had a small pipe and then a transition to a big pipe, and you wouldn't be able to use the Darcy-Weisbach equation with 2 different diameters. It can only be used in sections where the diameter is constant so that the velocity is constant within that section. And if you have water flowing through a pipe, then the slope of the energy grade line is independent of the physical slope of the pipe. But that won't be true in open channel flow. Okay, so shear stress is newtons per meter squared. That's the units of shear stress. Well, we can kind of do a transformation of shear stress to get its units in terms of velocity if we combine shear stress with an estimation of energy loss due to pipe friction using the Darcy-Weisbach equation. So what this is saying is if we have the energy loss characterized by the shear stress, and then we set that equal to the Darcy-Weisbach equation, we can rearrange so that we have the friction factor on one side of the equation, the shear stress on the other, and this left-hand side of the equation, if we just were to look at what are the units on the left-hand side of that equation, the shear stress is newtons per meter squared, and the density would be kilograms per cubic meter. So combining the two together, we've got newtons per meter squared due to the shear stress, and then the inverse of the units of density, so now meters cubed in the numerator, kilograms in the denominator. This shows you that the units of this term is meters squared per second squared. And so someone got the bright idea, wow, that's pretty close to meters per second, which is a velocity. So if we took the square root of that side of the equation, we could call it shear stress, we could call it shear velocity, and it would have units of meters per second. So the reason why shear velocity is important is that sometimes the flow conditions can be summarized really easily with the shear velocity, and it'll allow you to calculate the friction factor F. So this is just a relationship. I think this is coming up in the homework again, where you'll be given the shear velocity and estimating the friction factor from that, or vice versa. It's just sort of one of those things that you need to go through once so that you know it's there, but it's not, the shear velocity isn't something that designers would talk about very frequently. It doesn't come into application very often, but it would maybe give you some insight into how friction factors are estimated and how those things are measured in the first place. Okay, this is a trapezoidal channel, and trapezoidal channels give us a few challenges having to do with the geometry. And so you'll notice here that the side slopes are defined in terms of 1 unit of vertical and t units, 1 unit of horizontal and t being the vertical parameter. I just said it the wrong way. 1 is vertical, t is horizontal. So this side slope, a pretty typical side slope would be 1 to 2. And the reason for that is if you make it really steep and it's not lined with concrete or asphalt, then it's not going to be a stable slope. But if it's just a grass-lined channel, you can usually maintain a 1 to 2 side slope. Remember that we defined shear stress in terms of the slope of the energy grade line. We can use those same relationships in open channel as well. And so if we want to find out what is the slope of the energy grade line and how that affects the shear stress that's acting on the side of the embankment or the bottom of the channel, we can calculate the shear stress and compare it to like the cohesive strength of the soil, for instance. Now, eventually you're going to get to the point where you're going to need to calculate things like the geometric parameters here. So hydraulic radius is area divided by wetted perimeter. So if you have a trapezoidal channel, the area that we're talking about can be broken up into a couple of different segments. So here's our water, there's the side triangles, and then there's the rectangle in the middle. And so the bottom width B and the depth of flow is defined as Y. And so the area is going to be these side triangles plus the rectangle in the middle. And if we have 1 to t, then what that means about this length, that distance can be calculated with the square root of y squared plus ty squared. So if you have some depth that's given, the flow depth is known y, then that'll allow you to calculate the length of the sides. And so the area of flow is b times y, so that's the area of the rectangle in the middle, plus y times ty. So the depth, and then this distance is t times y. So if it's a 1-to-1 side slope, then it would be 1 times y. So this side triangle would be 1/2 of y squared, and this would be the other half of y squared. So you put those two triangles together, and it would be like a square having an area of y squared. So that's the cross-sectional area. Wetted perimeter is B, the bottom distance, where water is touching that perimeter and water is also touching both of the sides as well. So it is B plus 2 times the square root of y squared plus ty squared. In other words, that is b plus 2y square root of 1 plus t squared. We'll revisit the trapezoidal geometry several times through the semester, but I wanted to give you this first look at it because there's a couple of problems in the homework that ask you to relate the shear stress with like a width and depth of flow. So I wanted to give you these formulas for area and wetted perimeter so that you can calculate the hydraulic radius. And so just to sum it all up, the hydraulic radius, R, is by plus ty squared divided by b plus 2y is 1 plus t squared. So here's the hydraulic radius of a trapezoidal open channel. It's also in your book. I think in chapter 10 there's a table that has a bunch of geometric parameters for things like cross-sectional area, wetted perimeter, hydraulic radius for a variety of shapes. But the trapezoidal shape is really important in hydraulic engineering. All right, so we're out of time. That's all I've got for you today. Just remember that the homework's available. I'd encourage you to start taking a look at that. There are problems that you can solve on it already. If you'd like to take another treat on your way out, please do. And I will see you in class on Friday.